26,000 light-years from where you're lying right now, something sits in perfect darkness, waiting. No light escapes it. No signal explains it. Stars twist and bend around it, like moths circling a flame they can never touch, spinning faster than anything should be able to spin, held captive by a force with no visible source, no surface, no edge you could ever stand on. 4 million times the mass of our Sun, compressed into a space smaller than the distance between us and the nearest star, hidden behind a wall of dust so thick that for most of human history, no one even knew it was there. Tonight, you are going to come face to face with the thing that quietly commands our entire galaxy. The thing every star, every planet, every one of us has been slowly circling since before you were born. Close your eyes for a moment and picture the simplest thing you have ever done. Stepping outside on a clear night, tilting your head back and looking up. No telescope, no equipment, just you, standing still, staring into a sky scattered with light. It feels like one of the oldest, gentlest things a person can do. And yet, without realizing it, you're looking directly at one of the greatest mysteries our species has ever tried to solve. Somewhere in that quiet spread of stars lies an answer that took us thousands of years and countless failed guesses to even begin to understand. But to understand what waits there, we have to go back. Not to telescopes, not to satellites, not to control rooms filled with humming machines. We have to go back to the very beginning of human curiosity itself, to a time before anyone had the tools to ask the question properly. Long before instruments, before mathematics, before anyone had a name for a galaxy, people were already looking up. They were already noticing that one part of the sky looked different from the rest. On a clear night, far from any city, you can still see it today. A pale, hazy band stretching across the darkness, like a soft trail of smoke someone forgot to clean away. Ancient cultures had their own stories for it. Some called it a river of milk spilled across the heavens. Others believed it was a path walked by spirits, or a bridge connecting the world of the living to the world beyond. They did not know what they were looking at. How could they? They had no way of knowing that this faint band of light was not a river, or a road, or a trail of smoke at all. It was our own galaxy, seen from the inside, its billions of stars blurring together into a single pale smear because we are embedded within it, looking out through its own crowded disk. Here's the thing most people don't realize. When you look at that hazy band, you're not looking at some distant object out there in space. You're looking at home. You're looking at the very structure you live inside, the same structure that holds our sun, our planet, and every person you have ever known. It is easy to forget that the Milky Way is not something separate from us. It is the room we are standing in. We simply cannot see its walls because we are too close, too small, and too deeply embedded within it to notice its true shape. And if you follow that pale band with your eyes tracing it slowly across the sky, it grows brighter in one particular direction, toward a small, unassuming patch of stars that ancient astronomers eventually named Sagittarius after the archer. To the naked eye, there is nothing unusual there. No flash, no glow, no obvious sign that anything important is happening. Just more stars packed slightly closer together than anywhere else, glowing a little more densely, a little more insistently, as if something behind them were pulling them all toward the same invisible point. For most of human history, that was the end of the story. People noticed the brightness. They gave it names, wove it into myths, used it to mark seasons and guide ships across oceans. But nobody asked what was actually there, because nobody had reason to think there was anything to ask about. It looks like more stars. It looks like more of the same softly burning light scattered everywhere else in the sky. There was no reason yet to suspect that this particular patch of darkness was different from any other. Here is the number that changes everything. That patch of sky, the one glowing faintly toward the archer's arrow, sits roughly 26,000 light years away from where you're lying right now. Let that settle for a moment. Light, the fastest thing that exists, the thing that crosses your entire room in a fraction of a second, would need 26,000 years to travel from there to here. 26,000 years, longer than recorded human history, longer than agriculture, longer than cities, longer than writing itself. And that distance is not even close to the edge of our galaxy. It is the distance to the middle of it. Think about what that really means. Every star you have ever wished upon, every constellation you have ever learned to recognize, every point of light visible to the naked eye on a clear night, all of it lies far closer to us than that one patch of sky towards Sagittarius. We are, in a very real sense, standing near the outer edge of something enormous, gazing toward its center from a great distance, the way a single grain of sand near the shore might wonder what lies at the middle of an ocean it cannot see across. And there is something else, something almost frustrating about that direction. Even with the most powerful telescopes ever built, even now, we cannot simply look straight at it and see what waits there. Between us and the center of our galaxy lies an enormous, sprawling curtain of gas and dust, spread across tens of thousands of light years, thick enough to swallow ordinary light before it ever reaches us. It is not empty space between here and there. It is fog, endless, star-obscuring fog, drifting silently through the galactic disk, hiding whatever lies at the heart of it all. So the question that ancient skywatchers never even thought to ask becomes, for us, almost impossible to ignore. What is actually there? What sits behind that curtain of dust at the exact center of the structure we call home? Something is pulling entire arms of stars into a slow, patient spiral around it. Something has enough influence to shape the orbit of everything in this galaxy, including our own sun. And for nearly the whole of human history, we had no way of even beginning to look. You already know in a quiet corner of your mind that eventually we found a way to look. Eventually, someone built an instrument sensitive enough to see through fog that light itself could not cross. But that story does not begin with an answer. It begins with people slowly realizing that the fog itself was the first clue, that the very fact something was being hidden meant something worth hiding was there to find. And so, long before we ever had a name for what waits at the center of the galaxy, we simply had a direction, a patch of sky, a quiet, persistent glow toward the archer, patiently waiting for someone curious enough and patient enough to finally learn how to see through the dark. Long before anyone understood what that patch of sky truly was, entire civilizations built their calendars around it. In ancient Mesopotamia, priests and astronomers tracked the slow drift of that dense, glowing region night after night, year after year, using it to mark the turning of seasons. They had no concept of galaxies, no notion of light years, no way to measure distance beyond what the eye could estimate. What they had was patience and the quiet discipline of watching the same patch of darkness for a lifetime, recording what it did and passing that knowledge down to the next generation of watchers. The Babylonians were among the first to give that region of sky a lasting identity, weaving it into the shape of a hunter, an archer with a drawn bow, aiming an arrow toward the brightest part of that hazy band. Centuries later, the Greeks inherited and refined the idea, and the constellation Sagittarius took the form we still recognize today. To them, the brightness clustered near the archer's arrow was simply a denser gathering of stars, remarkable but not yet mysterious. Nobody suspected that this particular point in the sky held any more significance than any other bright patch above their heads. And yet, there was something quietly persistent about the way ancient people kept returning to it. Sailors used the pale band above the archer to orient themselves at sea, long before compasses existed. Farmers used its position to judge when to plant and when to harvest. Priests built temples aligned with its seasonal path across the sky. across wildly different cultures, separated by oceans and centuries, with no way to communicate with one another, people kept noticing the same thing. That one region of the sky simply refused to look ordinary, no matter how many times they studied it. By the time the Greek astronomer Ptolemy compiled his star catalogue in the 2nd century, cataloguing over 1,000 stars visible to the naked eye, the brightness near Sagittarius had already earned its own quiet reputation. Ptolemy and the astronomers who followed him could measure the positions of stars with impressive precision for their time, tracking their rising and setting with careful mathematics. But precision in position was not the same as understanding in substance. They could tell you exactly where the glow was. They could not tell you what it actually was made of, or why it clustered so densely in that one direction and nowhere else. For well over 1,000 years after Ptolemy, that gap in understanding barely changed. Astronomers across the Islamic world, from Baghdad to Cordoba, refined star catalogues further, correcting errors, adding new observations, building instruments of remarkable sophistication for measuring angles in the sky. They gave many stars the names we still use today, but even their finest instruments, however carefully built, were designed to measure position and brightness, not composition. The pale band above Sagittarius remained exactly what it had always been to human eyes, a soft, unresolved glow, its true nature completely out of reach. Everything changed, quietly and without fanfare, in the early 1600s. A relatively new invention, a simple tube fitted with curved pieces of glass, had begun circulating among astronomers in Europe. Most people who first heard of it assumed it was a novelty, useful for looking at distant ships or watching birds. Nobody yet understood that this modest device was about to dismantle thousands of years of assumptions about the night sky all at once, without warning. In the year 1609, an Italian astronomer turned one of these primitive telescopes toward that same familiar, hazy band stretching across the sky, the one people had been staring at with the naked eye since before written history began. What he saw through the eyepiece should have been impossible, according to everything astronomers believed at the time. The soft, continuous glow that generations had assumed was some kind of luminous cloud or vapour or celestial mist was not a cloud at all. It was not smoke, it was not fog drifting somewhere above the world. It was stars, thousands upon thousands of individual stars, packed so closely together that to the naked eye, unaided by any instrument, they simply blurred into a single, continuous smear of light. Where ancient astronomers had seen one soft haze, the telescope revealed countless separate points, each one its own distant sun, burning quietly in the dark, invisible without help, yet undeniably real once properly observed. It was, without exaggeration, one of the most disorienting discoveries in the history of astronomy. An entire feature of the sky that humanity had stared at for millennia was not what anyone had assumed it to be, and once that realization settled in, a far more unsettling question followed close behind it. If that pale band across the sky was actually an uncountable multitude of individual stars, packed together in some kind of vast structure, then what exactly was that structure? Where did it begin and where did it end? And why, out of every direction a person could look, did the stars cluster so densely toward that same patch of sky near Sagittarius? The very same direction ancient priests and sailors had been quietly drawn to for thousands of years, without ever knowing why. Here is the part that took astronomers far longer to work out than you might expect. It would take more than 3 centuries after that first telescope observation before anyone truly understood that we ourselves were living inside this structure, embedded within its stars rather than looking at it from some vantage point outside. It would take even longer still before anyone dared to ask what might be sitting at its exact centre, holding it together, shaping the paths of the stars around it. For now, in this earlier chapter of the story, all that existed was a growing, quiet unease, a sense that the brightness towards Sagittarius was not simply denser, it was pointing towards something, and nobody yet had any idea what that something might be. It would take astronomers a very long time to arrive at the answer, but eventually, one piece of the puzzle became clear. The pale band of stars stretching across the sky was not just a random scattering of distant suns. It was a disk, a vast, flattened structure, spinning slowly, with our own sun embedded somewhere within its arms, far from the centre, far from the edge, tucked quietly into one of its outer regions. Once astronomers understood that we were living inside this structure, rather than observing it from outside, a new and far more frustrating problem revealed itself almost immediately. If you're standing inside a disc-shaped structure, looking toward its centre, you are not just looking across open space. You are looking through the thickest part of it. Every star between you and the middle of the galaxy lies directly in your line of sight, layered one behind another, stretching back tens of thousands of light years. And stars are not the only thing filling that space. Scattered between them, drifting slowly through the disk is something far less glamorous, far less discussed, and far more disruptive to anyone trying to see clearly. Dust, not dust in the way you might picture it, not the fine grey powder that settles on a shelf in a quiet room. Interstellar dust is different. It is made of microscopic grains of carbon and silicate, remnants left behind by dying stars, scattered across space over billions of years. Individually, each grain is smaller than anything you could see with your own eyes, but spread across tens of thousands of light years, layered into vast clouds by gravity, that dust becomes something else entirely. It becomes a barrier, a curtain drawn across the one direction astronomers most wanted to see through. Here's the thing most people don't realize about that barrier. It does not block light evenly. It is especially effective at scattering and absorbing visible light. The very same kind of light your eyes are built to detect. A star that would appear brilliant if it were sitting nearby, unobstructed, can become almost completely invisible if enough dust lies between it and you. Multiply that effect across the entire width of the galactic disk, across tens of thousands of light years of scattered clouds, and you are left with something astronomers eventually gave a rather blunt name. They called it the zone of avoidance, a region of sky so thoroughly obscured that for a long time it was easier to study almost anything else in the universe than to study what lay directly at the heart of our own galaxy. Think about how strange that really is. By the early 20th century, astronomers had already measured the distances to other galaxies, some of them millions of light years away. They had photographed spiral arms belonging to entirely separate collections of stars, systems we would never visit, never touch, existing far beyond anything human beings could ever hope to reach. And yet, the exact center of our own galaxy, the one structure we are actually embedded within, the one whose gravity governs the orbit of our own sun, remained essentially invisible. It was, in a very real sense, easier to study a stranger's home in perfect detail than to see clearly into the middle of our own. That contradiction did not sit well with astronomers of the time. If anything, it deepened the mystery rather than settling it. Every clue available suggested that whatever sat at the center of the galaxy had to be significant. Stars appear to orbit that region the way planets orbit a sun. Radio signals, once astronomers eventually learned to detect them, seemed to concentrate there with unusual intensity. And yet, decade after decade, anyone who pointed an ordinary telescope directly at that patch of sky near Sagittarius was rewarded with almost nothing. A dim haze, a faint reddish smear, occasionally nothing visible at all, swallowed completely by the dust in between. Some astronomers, frustrated by the limits of visible light, began wondering whether the problem was not the target itself, but the tool being used to study it. Visible light, the narrow band of the spectrum that your eyes are built to perceive, makes up only a small fraction of the full range of energy travelling through the universe. Beyond what human eyes can see, there exist other forms of light entirely. Waves stretched longer than red light. Waves compressed shorter than violet, most of them completely invisible to unaided human vision, yet just as real, just as capable of carrying information across the emptiness of space. If visible light could not pass through the dust surrounding the galactic centre, perhaps some other form of light could. It was, in many ways, a shift in imagination as much as a shift in science. Astronomers began to consider that the answer to their oldest question, the one people had been quietly circling since the earliest Mesopotamian sky watchers, might not require a bigger telescope built to see the same kind of light more clearly. It might require an entirely different kind of eye altogether, one sensitive to wavelengths the human body was never designed to notice. That idea, radical for its time, would take decades to fully develop into working technology. But it planted something important. A belief, however uncertain, that the galactic centre was not permanently unreachable. It was simply hidden behind the wrong kind of light. Somewhere beyond that curtain of dust, something was still there, still exerting its influence, still shaping the slow rotation of everything around it, patiently waiting for someone to build an instrument capable of seeing past the fog rather than simply staring helplessly into it. And so, by the early decades of the 20th century, the mystery had shifted shape without becoming any less unsettling. It was no longer a question of whether something significant occupied the centre of the galaxy. Nearly everything astronomers had learned about the disk, its rotation, its structure, its gravity, pointed toward the certainty that something was there. The question had become narrower, and in some ways more haunting. Not what is hidden, but how, after thousands of years of looking up, could humanity finally learn to see through the one wall the universe had placed directly between us and the answer. The answer, when it finally arrived, did not come from an observatory built to study the stars. It came from a young engineer working for a telephone company, trying to solve a much smaller, much more practical problem. In the early 1930s, long-distance telephone calls sent across the Atlantic Ocean were plagued by static, bursts of interference that disrupted conversations for reasons nobody fully understood. A researcher named Karl Jansky was given the task of figuring out where that static was coming from, so that engineers could design better equipment to avoid it. Jansky built a large rotating antenna, an unusual-looking contraption of wood and wire mounted on wheels, designed to sweep slowly across the sky and record radio interference from every direction. Most of what he detected was exactly what he expected: static from distant thunderstorms, static from nearby electrical equipment, the ordinary background noise of a world humming with machinery and weather. But buried within his recordings was something else entirely, a faint, steady hiss that did not behave like storms or electrical interference at all. It rose and fell on a schedule that had nothing to do with the weather on Earth. At first, Jansky assumed the pattern was connected to the sun, since the hiss seemed to follow a roughly daily rhythm. But as he collected more data, month after month, he noticed something the sun could not explain. The timing of the signal was drifting, slowly shifting earlier each day by about 4 minutes. That small, seemingly meaningless detail turned out to be the key to the entire mystery. A shift of 4 minutes each day is not the rhythm of the sun, it is the rhythm of the stars, the signature of an object fixed against the distant background of the galaxy rather than tied to Earth's relationship with its own sun. When Jansky traced the source of that faint, persistent hiss to its exact position in the sky, he found it coming from one direction above all others, toward the constellation Sagittarius, toward the very same patch of stars that ancient priests had once aligned their temples with, that sailors had once used to navigate open oceans, that generations of astronomers had stared at through telescopes, only to find their view swallowed by dust. Except Jansky had not used a telescope built to capture visible light at all. He had built, almost by accident, the first instrument in human history capable of detecting energy pouring out of the galactic centre that no eye and no ordinary telescope could ever hope to see. Here's the thing most people don't realise about that moment. Jansky had no interest in astronomy. He was not searching for the heart of the galaxy. He was trying to stop annoying static from interrupting phone calls. And yet, in the process of solving a mundane engineering problem, he had opened an entirely new window onto the universe, one built not from glass lenses, but from radio waves, a form of light stretched far longer than anything visible to the human eye, capable of passing straight through the dust that had blocked every attempt to see the galactic centre for thousands of years. The scientific community's reaction to Jansky's discovery, published in 1933, was surprisingly muted. Astronomers of the time were focused almost entirely on visible light, and the idea of studying the sky using invisible radio waves seemed, to many, like a curiosity rather than a genuine breakthrough. Jansky himself moved on to other projects, and for nearly a decade, almost nobody followed up on what he had found. The signal from the direction of Sagittarius sat quietly in scientific journals, waiting for someone curious enough to take it seriously. That someone turned out to be an amateur astronomer named Grote Reber, working alone in his backyard, who built the world's first purpose-designed radio telescope using little more than sheet metal and personal savings. Where professional observatories had ignored Jansky's findings, Reber spent years mapping the sky in radio waves entirely on his own, confirming and refining what Jansky had stumbled upon. His maps showed unmistakably that the strongest radio emission in the entire sky came from that same direction, deep within the dust-obscured heart of the galaxy, exactly where visible light telescopes had always failed. By the 1950s, radio astronomy had finally begun to earn serious attention, developing rapidly as governments and universities invested in larger, more sensitive instruments. Massive dish-shaped antennas began rising from fields in England, Australia, and the United States, each one designed to capture radio waves too faint for Jansky's original wooden contraption to ever detect. Slowly, methodically, astronomers began building a picture of the galactic centre that visible light had never allowed. Not a picture made of light you could see with your eyes, but one built entirely from waves invisible to human vision, patiently gathered and translated into maps and images. What those early radio maps revealed was both exciting and deeply strange. The radio emission from the direction of Sagittarius was not spread evenly across a wide region, the way you might expect from ordinary stars scattered throughout space. It appeared concentrated, unusually intense, coming from a surprisingly small and specific area. Almost everything about ordinary astrophysics suggested that such a small region should not be capable of producing that much energy. Something in that tiny patch of sky was generating far more radio emission than any known collection of ordinary stars should be able to produce on its own. And so, by the middle of the 20th century, humanity had finally managed to see past the wall of dust that had hidden the galactic centre for the entirety of recorded history. But seeing past the dust did not mean understanding what was actually there. If anything, the radio observations only deepened the unease. Something small, something intensely bright in radio waves, something inexplicably powerful, sat exactly where the ancient glow towards Sagittarius had always pointed. Astronomers now had a location. They now had unmistakable evidence that something extraordinary was there. What they still did not have, and would not have for years to come, was any real idea of what that something actually was. By the early 1970s, radio astronomy had matured into a precise and powerful science, capable of resolving details that Carl Jansky's original wooden antenna could never have detected. Observatories around the world had spent decades refining their instruments, learning to filter noise, sharp in resolution, and pinpoint sources of radio emission with increasing accuracy. The broad, blurry patch of radio brightness towards Sagittarius, once a single, unresolved glow, was beginning to reveal finer and finer structure. Astronomers were no longer satisfied with knowing that something powerful sat in that general direction. They wanted to know exactly where down to the smallest possible point. The year was 1974. At the National Radio Astronomy Observatory in the United States, two astronomers, Bruce Balich and Robert Brown, turned a newly upgraded radio interferometer toward the galactic center, hoping to resolve the mysterious emission into something more precise than earlier, cruder instruments had ever managed. What they found, buried within the wider glow of radio noise, was a single, compact, unusually bright point. Not a broad region, not a diffuse cloud of gas radiating gently across a wide area. A single, tightly concentrated source, smaller and more intense than anything else nearby. Here's the thing most people don't realize about how that discovery was named. Radio astronomers of the time followed a fairly simple naming convention, labeling bright sources within a constellation using letters, starting from the beginning of the alphabet for the most prominent ones. Since this compact new source sat within the boundaries of Sagittarius and stood out as the most striking feature within it, it received the designation Sagittarius A. But as instruments grew sharper still, astronomers realized that this compact source contained an even smaller, even more extreme point buried at its very center, distinct from the surrounding material. That innermost point earned its own name, Sagittarius A star, written with an asterisk, a small mark that would come to represent one of the strangest objects in the observable universe. What made Sagittarius, a star so unusual, was not simply that it was bright. Many objects in the galaxy shine brightly in radio waves. What startled astronomers was how small the source appeared to be, and how much energy was pouring out of that tiny region. Estimates suggested the emitting area was no larger than our own solar system, a genuinely tiny space by galactic standards, smaller than the distance between the Sun and its outermost planets. And yet, from that cramped, almost unimaginably small region, energy was radiating outward with an intensity that made no sense for any known type of star or cluster of stars crammed into so little space. Think about the scale of that contradiction for a moment. An ordinary star, even an extremely large one, occupies a certain amount of space roughly proportional to how much energy it produces. Cramming that much brightness into a region smaller than our solar system violated every expectation astronomers had built up over centuries of studying ordinary stars. Something about Sagittarius A star was fundamentally different from anything catalogued before. It behaved less like a star and more like the signature of some far stranger, far more compact kind of object, one whose true nature nobody could yet confidently describe. At the time, theoretical physicists had already been quietly discussing a strange and unsettling idea for decades, one that had emerged from Einstein's equations of general relativity long before anyone had observational evidence to support it. The idea that matter, under the right extreme conditions, could collapse so completely under its own gravity that it would crush itself into an infinitely small point, surrounded by a boundary from which nothing, not even light, could ever escape. For most of the 20th century, this idea existed mostly as a mathematical curiosity, a strange consequence of equations that many physicists assumed nature would somehow avoid in reality. Few believed such an object could actually exist, let alone that we might one day detect one. But the discovery of Sagittarius A star, small, immensely energetic, and utterly unlike any known star, gave that mathematical curiosity a possible home in the real universe. Astronomers began to quietly wonder, almost reluctantly at first, whether the compact object at the heart of our galaxy might be exactly the kind of extreme, collapsed structure that theorists had been describing on paper for decades. It was, understandably, not an idea the scientific community rushed to embrace. Extraordinary claims require extraordinary evidence, and in the mid-1970s, there was no way yet to directly measure how much mass that tiny region actually contained. What astronomers needed was a way to weigh Sagittarius A star, not by looking at it directly, since it produced no visible light at all, but by observing its effect on whatever happened to be nearby. If something with enormous mass truly sat at that location, its gravity should be strong enough to influence the motion of nearby stars and gas, bending their paths, accelerating their speeds, betraying the presence of something invisible through nothing more than the way surrounding objects moved around it. It was the same basic principle sailors once used to detect unseen currents in the ocean, judging the presence of something powerful and hidden by watching how everything nearby responded to it. Throughout the remainder of the 1970s and into the 1980s, astronomers slowly began developing the tools needed to make exactly those kinds of measurements. It would not happen quickly. Observing individual stars close enough to the galactic center to reveal meaningful motion required technology that did not yet exist in a form precise enough for the task. But the target had at last been identified with confidence. A name had been given to the mystery that priests, sailors, and astronomers had been circling for thousands of years without ever knowing its true nature. Sagittarius, a star, small, silent, extraordinarily bright in wavelengths invisible to human eyes. And now, for the first time in history, waiting to be weighed. By the early 1990s, two independent teams of astronomers, one working in Germany, the other in the United States, had begun a project that would have been unthinkable just a few decades earlier. Rather than trying to observe Sagittarius A star directly, since it produced no visible light at all, they decided to watch the stars orbiting closest to it. If enormous invisible mass truly sat at that location, the stars nearby should betray its presence through their motion, tracing paths shaped by a gravity far stronger than anything an ordinary collection of stars could produce. The challenge was staggering. The stars near the galactic center are packed far more densely than stars anywhere near our own solar system, crowded together and obscured by the same thick dust that had frustrated astronomers for centuries. Observing them clearly required some of the most advanced infrared telescopes ever built, along with a technique called adaptive optics, which uses flexible mirrors adjusting many times per second to cancel out the blurring caused by Earth's own atmosphere. Without this technology, the stars near Sagittarius A star would have remained nothing more than a smeared indistinct blur, impossible to track individually across time. Year after year, the two teams patiently photographed the same tiny patch of sky, building up a slow, careful record of exactly where each star sat relative to its neighbours. It was, in many ways, a profoundly unglamorous kind of science. No dramatic breakthroughs, no sudden flashes of insight, just the quiet accumulation of data, one observation at a time, across years that eventually stretched into decades. And slowly, almost imperceptibly, at first a pattern began to emerge from the numbers. The stars nearest to Sagittarius, our star, were not sitting still. They were moving, and they were moving fast. One particular star drew more attention than any other. Astronomers eventually named it S2, a relatively ordinary-looking star by the standards of its type, notable only because of its extraordinarily close orbit around the galactic center. Watching S2 across repeated observations revealed something that defied ordinary expectations of how stars behave. Rather than drifting slowly, the way distant stars typically appear to from Earth, S2 was clearly tracing out an orbit, curving through space the same way a planet curves around a sun, except at speeds that seemed almost impossible for anything to survive. Here's the thing most people don't realize about just how fast S2 was moving. At the closest point in its orbit, S2 reaches speeds exceeding 7,500 kilometers per second. To put that in perspective, at that speed, you could cross the entire distance between the Earth and the Moon in less than a minute. S2 was completing this staggering high-speed loop around an apparently empty point in space, invisible to every telescope pointed at it, over a period of roughly 16 years, an astonishingly short orbital period for anything located so far from any visible source of gravity. Think about what that really means. Planets in our own solar system take years, sometimes centuries, to complete a single orbit around our Sun, and our Sun is a star with clearly visible mass, sitting right there for anyone to see. S2 was completing an entire orbit in roughly the time it takes a person to grow from childhood into adulthood, circling something with no visible surface, no detectable light of its own, nothing an ordinary telescope could point to and call an object. Whatever S2 was orbiting had to possess an amount of gravity far beyond anything a normal star or even a dense cluster of ordinary stars could ever produce. As the two research teams continued tracking S2 and several other nearby stars over the following years, they were able to apply a formula that has existed since long before anyone imagined black holes might be real. The same basic law of gravity Isaac Newton described centuries earlier, when he first worked out how the Moon stays in orbit around the Earth. If you know how fast an object is moving and the size and shape of the path it traces, you can calculate the mass of whatever is holding it in that orbit, even if that central mass remains completely invisible to every instrument you own. When astronomers finally ran those calculations using the precise orbital data collected from S2 and its neighbouring stars, the result was almost too large to comprehend. The invisible objects at the centre of those orbits, the same object first detected as a strange radio source decades earlier, the same faint point ancient priests had unknowingly aligned their temples toward thousands of years before, appeared to contain the mass of millions of suns. Not one sun, not a handful of unusually large stars. Millions compressed into a region far too small for any ordinary collection of stars to occupy without becoming visible. This was not the kind of result scientists announce lightly. Both research teams spent years cross-checking their measurements, refining their instruments, and independently confirming their findings before publishing results with any confidence. Extraordinary numbers demand extraordinary scrutiny, and the implications of what they were finding were significant enough that neither team wanted to risk being wrong. But observation after observation, year after year, the answer kept returning the same unsettling conclusion. Something invisible, something impossibly compact, and something almost unimaginably massive sat exactly at the point every star in that region seemed to be circling. By the time their research matured into a confident, well-supported conclusion, astronomers had achieved something that would have seemed like pure fantasy to the ancient sky watchers, who first noticed a strange brightness towards Sagittarius. They had weighed an object they could not see, using nothing more than the motion of stars orbiting around it in the dark. The number they arrived at was staggering enough to demand its own explanation, one that would take the story of the galactic centre somewhere even stranger than anyone had previously dared to imagine. When the two research teams finally combined decades of careful observation into a single, confident figure, the number they arrived at was 4,400,000 times the mass of our Sun. Take a moment to actually sit with that. Not 4 million stars scattered across a wide region of space, each contributing a small amount of gravity to the whole. 4,400,000 times the mass of our own Sun, concentrated into a single, invisible point, smaller than the distance between our Sun and its nearest orbiting planet. To understand how strange that really is, think about our own Sun for a moment. It already accounts for more than 99% of all the mass in our entire solar system, an object so large that over 1 million planets the size of Earth could fit inside it, and yet According to years of careful measurement, whatever sits at the center of our galaxy contains the equivalent mass of over 4 million objects, like our Sun, somehow packed into a space you could comfortably fit inside the orbit of Mercury. It is difficult to overstate how much of a contradiction that number represents. Here's the thing most people don't realize about mass on that scale. When you increase the amount of matter in a region, without increasing the space it occupies, you're not simply making something heavier, you're making it fundamentally different. A pile of sand does not behave the same way as a mountain of solid rock, even if you could theoretically compress enough sand to match the mountain's weight. At some point, cramming enough mass into a small enough space stops behaving like a bigger version of the same thing and starts behaving like something the universe has never produced before under ordinary conditions. Astronomers understood this problem well before they ever confirmed the mass hidden at the galactic center. Stars, no matter how large, have a natural limit to how tightly they can be packed together before something has to change. Push enough stars into a small enough volume, and their combined gravity begins to overwhelm the forces that normally keep matter apart. Atoms cannot simply be squeezed indefinitely without consequence. At some threshold, matter runs out of ways to resist being crushed further, and the object collapses inward on itself. Not gradually, but in a process that, once it begins, cannot be stopped by anything known to physics. Think about what 4,400,000 solar masses squeezed into that tiny region actually implies. It rules out an ordinary star, since no star, however massive, could remain stable while containing that much matter in so little space. It rules out a dense star cluster too, since stars packed that closely together would collide and merge with catastrophic frequency, producing visible flashes of light that instruments would have detected decades ago. Every conventional explanation astronomers could imagine, every known category of astronomical object, failed to account for both the mass and the size of whatever occupied that single point. That left only one remaining possibility, the same possibility physicists had been quietly discussing since Einstein's equations first suggested it decades earlier. An object whose gravity had become so overwhelming that it had crushed itself completely, collapsing past every point where matter normally resists further compression, shrinking down towards something with essentially no size at all, while somehow retaining every bit of its original mass. Not a star, not a cluster, something else entirely, a category of object that, until this discovery, had existed mostly as an unsettling mathematical curiosity rather than a confirmed feature of the real universe. Analogies help here, because raw numbers this large tend to slide past the mind without truly registering. Imagine taking every grain of sand on every beach across the entire planet and somehow compressing all of it down into a space smaller than a single grain. That is roughly the kind of transformation we're talking about. Matter that should occupy an enormous volume, instead crushed into something almost inconceivably small, its outward appearance giving no hint whatsoever of the staggering quantity of material hidden within it. And yet, despite containing more mass than 4 million suns combined, this object remained, and remains today, completely invisible to ordinary telescopes. No light escapes it. No visible surface reflects sunlight the way a planet does. No glow betrays its presence, the way a star's own nuclear furnace lights it from within. Everything astronomers knew about it, they had learned indirectly, by watching how stars like S2 bent and curved around a point that offered no light of its own, no signal, no visible confirmation beyond the undeniable mathematics of gravity pulling on everything nearby. This is the part of the story where the tone of the research quietly shifted, from cautious skepticism towards something closer to unsettled acceptance. For most of the 20th century, many physicists had assumed that objects this extreme, capable of swallowing 4 million suns worth of mass into an essentially invisible point, were likely too strange, too extreme, to actually exist in the real universe. They belonged, many believed, in the realm of mathematics, not observation. The measurements coming from the galactic center suggested otherwise, and suggested it with a level of confidence that was becoming increasingly difficult to dismiss. By the early 2000s, the evidence had accumulated to the point where the scientific community could no longer treat this possibility as merely theoretical. Something with the mass of 4,400,000 suns, confined to a region smaller than our inner solar system, producing no visible light of its own, sat quietly at the exact center of the galaxy we call home. Every star in the Milky Way, including our own sun, was slowly circling that same hidden point. The way moths circle a flame they cannot see, drawn by a pull whose source remained, for now, defined only by numbers and not yet by any direct image, any confirmed shape, or any true understanding of what an object like that actually was. Once astronomers accepted what the numbers were telling them, they had to confront a term that had spent most of the 20th century sitting on the edge of respectable science. Black hole. It is a phrase so familiar now, so casually used in movies and conversation, that it is easy to forget how strange the actual concept truly is. A black hole is not a hole in the way you might picture one. It is not an empty gap, a tunnel, or an absence of something. It is, in a very real sense, the opposite. It is an overwhelming abundance of matter, compressed so completely that it fundamentally changes the shape of space around it. Here's the thing most people don't realize about what a black hole actually is. It has no surface. Not a hard surface like a planet. Not a gaseous surface like a star. Not even a churning, chaotic boundary like the edge of a storm. There is no floor to land on, no wall to strike, no outer shell you could ever touch and say, this is where the object begins. Every other object you have ever encountered, every rock, every planet, every star, has some kind of outer boundary separating it from the empty space around it. A black hole has none. It is simply mass folded into itself so completely that the very idea of a surface stops making sense. To understand how something can exist without a surface, it helps to think about what actually happens when matter collapses under its own gravity. Every object in the universe is held up by some force resisting the crush of its own weight. Planets are supported by solid rock and metal, resisting compression through sheer physical structure. Stars are held up by the outward pressure of nuclear fusion, an enormous furnace at their core, pushing back against gravity's constant pull inward. But when enough mass gathers in one place, and gravity grows strong enough, every one of those supporting forces eventually fails, one after another, with nothing left to take their place. When that final collapse happens, matter does not simply become very dense. It continues collapsing, essentially without limit, crushing itself down toward a single, infinitely small point that physicists call a singularity. All of that mass, 4,400,000 times the weight of our Sun, in the case of the object at our galaxy's centre, is theoretically compressed into a point with no measurable size at all. It is one of the strangest ideas in all of physics, a location where our best mathematical descriptions of the universe simply stop working, breaking down completely under the weight of their own predictions. Think about how deeply this challenges ordinary intuition. Everything you have ever touched, seen, or stood upon has some kind of physical extent, some amount of space it occupies, however small. A singularity, according to the mathematics describing it, occupies no space whatsoever, while still containing an almost incomprehensible amount of mass. It is a concept that many physicists, including some of the very people whose equations first predicted it, found deeply uncomfortable to accept. Nature, they assumed, surely had some mechanism to prevent something this extreme from actually forming in reality. And yet, decade after decade, observation after observation, every alternative explanation for the object at the center of our galaxy continued to fail. No known type of star could account for that much mass in that little space. No cluster of ordinary objects could remain stable while producing the gravitational effects being measured. Slowly, reluctantly, the scientific community arrived at the conclusion that nature apparently does allow this. Somewhere in the universe, under the right extreme conditions, matter really can collapse past every ordinary limit, crushing itself into something with no surface, no shape, and no comparison to anything else we have ever directly observed. This is where the calm, careful language of science begins to brush up against something closer to genuine unease. An object with no surface is, in a very real sense, an object with no boundaries in the way you understand boundaries. You cannot ask what it looks like up close, because there is no surface for light to bounce off of and reveal a shape. You cannot ask what it is made of, in the way you might describe the composition of a planet or a star, because whatever it once was made of has been crushed past the point where those descriptions still apply. It exists undeniably, and yet it defies almost every ordinary way we have of describing what an object actually is. Despite having no surface and producing no light of its own, this object still profoundly affects everything around it. Its gravity reaches outward for trillions of miles, shaping the orbits of stars like S2, bending the paths of gas clouds, quietly governing the slow rotation of the entire galaxy over the course of hundreds of millions of years. It is, in a strange way, defined entirely by its effect on everything else, rather than by any quality you could observe directly within itself. We know it exists because of what it does to its surroundings, not because we have ever seen it, touched it, or measured it directly in any conventional sense. Astronomers eventually settled on a specific category for this kind of object: a supermassive black hole, distinguishing it from smaller black holes that can form from the collapse of individual massive stars. Supermassive black holes, astronomers came to understand, are millions or even billions of times more massive than those smaller, stellar remnants, and appear to occupy the centers of galaxies rather than scattering randomly throughout them. The object at the heart of our own galaxy, the same faint radio source first detected decades earlier, the same invisible point that stars like S2 had been circling at extraordinary speeds, fit that description precisely. And so, by the early 2010s, the scientific consensus had shifted from cautious speculation to confident conclusion. A supermassive black hole sat at the exact center of the Milky Way, invisible, boundaryless, containing the crushed remains of what had once been the equivalent of 4,400,000 suns. Every star in our galaxy, every planet, every living thing that has ever existed within it, has spent its entire existence quietly orbiting this same silent, surfaceless void. Understanding that it existed, however, was only the beginning of an even stranger set of questions, still waiting to be answered. If a black hole has no surface, no floor, no wall, no shell you could ever land on, then it might seem reasonable to assume there is no true boundary to it at all, nothing you could point to and call an edge. And yet, there is a boundary, one every bit as real as the surface of a planet, even though it is not made of any physical material whatsoever. Astronomers call it the event horizon, and understanding what it actually is requires setting aside almost everything you assume about what a boundary is supposed to be. Here's the thing most people don't realize about the event horizon. It is not a wall, it is not a membrane, it is not made of matter in any form at all. Instead, it is a boundary defined entirely by speed, and by one very simple, very unforgiving rule. Beyond a certain distance from the crushed remains, at a black hole's center, the pull of gravity becomes so strong that escaping it would require moving faster than light itself. Since nothing in the universe can travel faster than light, that boundary marks the precise point past which nothing, absolutely nothing, can ever find its way back out. Think about how strange that really is. Everywhere else in the universe, if something falls into a gravity well, whether it is a spacecraft falling toward a planet or a comet swinging past a star, there is always, in principle, a way back out, given enough energy and enough speed. Cross the event horizon of a black hole, however, and that principle simply stops applying. It does not matter how powerful your engines are. It does not matter how much energy you have available. Once you cross that line, escape is not merely difficult. It becomes, according to everything we understand about the laws of physics, completely and permanently impossible. For the supermassive black hole at the center of our galaxy, astronomers have calculated the size of this invisible boundary with remarkable precision. Its event horizon spans roughly 25 million kilometers across, a distance that sounds enormous until you place it next to the 4,400,000 solar masses crushed inside it. To help make that scale feel real, imagine an object with the diameter of that boundary sitting where our Sun currently sits. It would comfortably fit within the orbit of Mercury, the closest planet to our Sun, occupying only a small fraction of the space our solar system actually spans. And yet, everything inside that comparatively modest boundary contains more mass than millions of suns combined. One of the most unsettling qualities of the event horizon is how utterly ordinary it would appear if you could somehow approach it safely. There is no dramatic visual marker hovering in space, no glowing ring warning you that you're approaching the edge of no return. Space itself, from a distance, simply looks like space, empty and dark, giving no obvious indication that anything unusual lies ahead. The danger is not visible. It is not something your eyes could detect and react to in time. It exists purely as a mathematical threshold, invisible until the moment it becomes inescapable. This is where the analogy of a waterfall becomes useful, one that physicists have used for decades to help explain something otherwise almost impossible to picture. Imagine a river flowing steadily toward a massive waterfall. Far upstream, the water moves gently, and a boat could easily turn around and paddle back against the current with only moderate effort. But as the boat drifts closer to the falls, the current accelerates, and at some specific point, the water begins moving faster than any boat could ever paddle against, no matter how powerful its engine. Past that point, the boat's fate is sealed, not because of some visible wall stopping it, but because the flow itself has become too strong to resist. An event horizon works in a remarkably similar way, except instead of water, it is space itself that is, in a manner of speaking, flowing inward faster and faster the closer you get to the black hole's center. Far from the black hole, space behaves normally, and anything moving through it can travel freely in any direction. But close enough to the boundary, the inward pull becomes so extreme that even light, moving at the fastest speed the universe allows, cannot make progress against it. Light does not merely struggle to escape near an event horizon. Beyond that boundary, it cannot escape at all, under any circumstances, for any reason. Think about what that truly means for the nature of the object sitting at the center of our galaxy. Everything we know about light, the same light that lets us see stars 26,000 light-years away, the same light that let ancient astronomers first notice a pale band stretching across the night sky, simply fails once it crosses this boundary. For the first time in this entire story, we encounter a location in the universe where the very thing that has allowed us to observe everything else, light itself, becomes powerless. It is a strange kind of finish line, a place where our oldest and most reliable tool for understanding the cosmos runs out of road entirely, and yet, despite marking the point beyond which nothing can return, the event horizon itself does not represent the true heart of the black hole. It is simply the outer boundary, the last place where escape is still theoretically possible before gravity's grip becomes absolute. Everything that has ever crossed that boundary, whether gas, dust, or perhaps someday a spacecraft venturing too close, continues falling further inward, toward the crushed, infinitely dense point resting at the very center. What happens during that final descent, and what it might mean for anything unfortunate enough to make that journey, is a question physicists have spent decades trying to answer, one that stretches our understanding of space, time, and reality itself to its absolute limit. For nearly half a century, everything astronomers understood about the object at the center of our galaxy had been learned indirectly. A strange radio signal, the motion of distant stars, careful calculations of mass, size, and gravity, built entirely from evidence and mathematics rather than direct sight. No human being and no instrument ever built had actually seen the object itself, or anything resembling an image of it. By the middle of the 2010s, a small and determined group of scientists decided that indirect evidence was no longer enough. They wanted a picture, and building one meant assembling something that had never existed before in the history of astronomy. The problem they faced was almost absurd in scale, capturing an image of something 26,000 light-years away, an object whose event horizon spans roughly 25 million kilometers, requires a telescope with a resolving power far beyond anything humanly possible to build as a single instrument. To photograph something that small at that distance, scientists calculated, you would need a telescope roughly the size of an entire planet. Since building a telescope the size of Earth was, obviously, not an option, the team behind the project chose a different approach entirely, one built on cooperation rather than construction. They called it the Event Horizon Telescope, though it was never actually a single telescope at all. It was a network, a coordinated collaboration linking radio observatories scattered across the entire globe, from the mountains of Chile to the ice sheets of Antarctica, from Hawaii to Spain to Mexico. By synchronizing these facilities to observe the exact same target at the exact same moment, using a technique that treats the combined data as though it came from one enormous dish the size of the Earth itself, scientists could achieve the resolving power needed to see something otherwise completely beyond reach. Here's the thing most people don't realize about how difficult that coordination actually was. Every observatory involved had to point at precisely the right target at precisely the right time, while dealing with its own local weather, its own equipment quirks, and its own technical limitations. Data from each site had to be recorded with atomic clock precision, since even a fraction of a second of misalignment could ruin the entire combined image. Once collected, the raw data, amounting to petabytes of information, more than could realistically be transmitted over the internet, had to be physically flown on hard drives to a central processing location for analysis. In April of 2017, the global network of telescopes turned toward two targets at once. One was a supermassive black hole in a distant galaxy called Messier 87, chosen partly because its enormous size made it a slightly easier target to resolve. The other was the object at the heart of our own galaxy, the same invisible point that stars like S2 had been circling for decades, the same faint radio source first detected in 1974. Processing the data from both targets took years of painstaking analysis, cross-checking, and verification, precisely because the implications of getting it wrong were enormous. The image of the black hole in Messier 87 was released first in April of 2019, and it stunned the world. A blurred, glowing ring of orange light wrapped around a dark, empty center, exactly matching what theoretical physics had predicted a black hole's shadow should look like. It was humanity's first direct visual confirmation that these strange mathematically predicted objects truly existed, captured not through imagination or calculation alone, but through an actual photograph, however faint and blurred it appeared. But the object at the center of our own galaxy proved far more difficult to photograph. Sagittarius A star is significantly smaller than the black hole in Messier 87, and material orbiting it moves so quickly, completing loops in a matter of minutes rather than days or years, that the image blurred and shifted even during the short observation windows. It took years of additional processing, new techniques, and painstaking verification before the team felt confident enough to release what they had found. That moment finally arrived in May of 2022. The image was, once again, a glowing ring of light surrounding a dark central shadow, this time smaller, dimmer, and considerably harder won than the first, but its meaning was every bit as profound. For the first time in human history, scientists were looking at direct visual evidence of the very object that ancient priests had unknowingly aligned their temples toward, that sailors had used to navigate without understanding, that radio astronomers had first detected as an unexplained hiss that had bent the orbit of a star named S2 at speeds exceeding 7,000 kilometers per second. 26,000 years after that light began its journey toward Earth, we were finally looking directly at the shadow it left behind. Think about what that photograph actually represents. The glowing ring is not the black hole itself, since the black hole produces no light of its own. It is superheated gas, swirling at tremendous speeds just outside the event horizon, bent and distorted by gravity so extreme that light itself curves around the darkness at the center. The dark region in the middle is the shadow of the event horizon, the boundary beyond which nothing, not even light, can ever return. We are not looking at the object, we are looking at the last visible trace of everything that surrounds the point where seeing simply becomes impossible. After thousands of years of watching a faint glow towards Sagittarius without understanding it, after Karl Jansky's accidental discovery of a strange radio hiss, after decades spent tracking the impossible speed of a star named S2, humanity had finally produced something no generation before ours had ever possessed. A picture, blurred, faint and hard-won, but undeniably real, standing as proof that the thing sitting at the center of our galaxy, the thing every star in the Milky Way has been quietly orbiting since long before human beings existed, was no longer only a number or a theory or a calculation. It had a shape, however dark. And now, for the first time, we had seen it. Once astronomers had confirmed the existence of Sagittarius A star, measured its mass, mapped its event horizon, and finally captured its shadow in a photograph, a deeper and stranger question began to take shape. Gravity this extreme does not simply pull on matter and light. According to Einstein's theory of general relativity, gravity this powerful also reaches into something far less tangible, something most people rarely think about at all. Time itself. Not time as a clock ticking on your wall, but time as a physical property of the universe, one that can stretch, slow, and bend depending on how close you happen to be to an enormous mass. Here's the thing most people don't realize about time. You tend to think of it as something fixed, something that moves forward at the same steady pace everywhere, for everyone, without exception. A minute here is a minute there. An hour spent near a mountain feels the same as an hour spent at sea. For nearly the entire span of human history, this assumption seemed completely reasonable, since nothing in ordinary experience ever suggested otherwise. But Einstein's equations revealed something deeply unsettling underneath that comfortable assumption. Time does not move at the same rate everywhere. It moves slower in the presence of strong gravity, and there is no gravity in our galaxy stronger than the gravity surrounding Sagittarius, a star. This effect, known as gravitational time dilation, is not merely a mathematical curiosity confined to black holes. It happens everywhere, all the time, at scales far too small for you to notice in ordinary life. Clocks on airplanes, flying at high altitude with slightly weaker gravity than clocks on the ground, tick at a very slightly different rate, a difference so small it can only be detected using instruments of extraordinary precision. Near an object like Sagittarius, a star, however, that tiny, imperceptible effect becomes anything but subtle. Close enough to its event horizon, time itself begins to slow dramatically, in ways that would feel deeply wrong to anyone able to experience it directly. Imagine, for a moment, a spacecraft approaching the boundary of Sagittarius A star, sending a steady radio signal back toward Earth once every second, like a heartbeat marking the passage of time. As that spacecraft drifted closer and closer to the event horizon, an observer watching from a safe distance would notice something deeply strange. The signals would not keep arriving once every second. They would begin arriving more slowly, every second, every 10 seconds, every minute. The spacecraft's clock from the outside perspective would appear to be running slower and slower, as though time itself were thickening, resisting its own forward motion the closer the ship came to the boundary. And here is the part that unsettles even physicists who have studied this for years. From the perspective of anyone actually aboard that spacecraft, nothing would feel unusual at all. Their own clock would continue ticking normally, 1 second following another, exactly as it always had. They would feel no slowing, no stretching, no sensation of time behaving strangely in any way. The distortion is not something you would experience from within. It only becomes apparent when comparing your own passage of time to someone else's. Someone sitting farther away, safely outside the reach of that extreme gravity. Think about what that really means. If time truly slows near Sagittarius A star, then in some very real sense, that region of space exists slightly out of step with the rest of the universe. A single day near the event horizon, whatever a day even means in a place so hostile that surviving there is likely impossible, could correspond to years, decades, or longer, passing everywhere else. Approaching close enough to a black hole's boundary is not simply dangerous because of gravity crushing you. It is dangerous because it would, quite literally, disconnect you from the ordinary flow of time experienced by everyone and everything you have ever known. This is not simply theoretical speculation dressed up for dramatic effect. Gravitational time dilation has been confirmed repeatedly, through decades of careful measurement, both here on Earth and through observations of stars orbiting close to massive objects, like Sagittarius A star. Scientists studying the star S2, the same star whose extreme orbital speed first helped reveal the black hole's staggering mass, have measured subtle shifts in the colour of its light as it swings closest to the galactic centre, shifts predicted precisely by the effects of both speed and gravity acting together on the flow of time itself. And this raises a question that tends to linger uncomfortably in the mind, long after you first encounter it. If time moves differently, depending on how close you are to enormous mass, then the very idea of a single, universal present moment, a single shared now, existing consistently everywhere across the universe, quietly falls apart. Somewhere near Sagittarius, a star, at this very instant, time might be crawling forward at a rate almost unimaginably slower than the rate you're experiencing right now. Listening to these words, lying quietly in the dark. There is no single clock ticking for the entire universe. There are countless clocks, each one running at its own pace shaped by the gravity surrounding it. Here's the thing most people don't realize about why this matters beyond pure curiosity. Time dilation near supermassive black holes is not just a strange side effect scientists find interesting to measure. It is direct, repeated, observable proof that gravity is not simply a force pulling objects together, the way people once casually assumed. It is something far stranger, a genuine warping of the fabric of space and time itself, curving reality around wherever mass happens to gather. Sagittarius. A star does not merely hold stars in orbit around it. It bends the very structure through which those stars and everything else nearby experience the passage of time. And so, as astronomers continue to study the region surrounding this strange, invisible object at the heart of our galaxy, they were no longer simply mapping gravity, or measuring mass, or photographing shadows. They were watching, in real and measurable terms, the fabric of the universe itself, bending and stretching under the influence of something with no surface, no light, and apparently its own strange relationship with time. What else, they began to wonder, might be hiding in that same warped extreme region, defying expectation in ways nobody had yet considered? As astronomers continued studying the strange, time-bending region surrounding Sagittarius, a star, they noticed something that at first glance seemed like a fairly ordinary observation. Scattered close to the black hole, tracing tight, fast orbits, similar to the star S2, were dozens of other stars, burning brightly, behaving in ways that appeared, on the surface, remarkably normal. But the more closely researchers studied these stars, the more one particular detail began to bother them. According to everything astronomers understood about how stars form, these particular stars simply should not exist where they were found. Here's the thing most people don't realize about how stars actually come into being. Stars form gradually, over enormous stretches of time, condensing slowly out of large, cold, relatively calm clouds of gas and dust. Gravity pulls these clouds inward, gently at first, allowing material to collect and compress over hundreds of thousands of years, until eventually the pressure and temperature at the center become great enough to ignite nuclear fusion. This process depends on stability. It depends on a relatively undisturbed environment where gas can gather quietly without being ripped apart before it ever has the chance to form something solid. The region surrounding Sagittarius. A star is about as far from that gentle, undisturbed environment as anything in the galaxy. Gravity near the black hole is so extreme that it exerts what astronomers call tidal forces, stretching and shearing anything nearby with tremendous violence. A loose, diffuse cloud of gas attempting to condense into a star that close to Sagittarius A star should, according to standard models, be torn apart long before gravity ever managed to compress it into anything resembling a functioning star. And yet, dozens of young massive stars sit remarkably close to the black hole, apparently having formed exactly where theory says they should not have been able to. Think about how strange this contradiction really is. Astronomers were not looking at ancient, ordinary stars that had simply drifted into a tight orbit after forming somewhere else, farther out in calmer surroundings. Many of the stars found near Sagittarius A star are young, by astronomical standards, and clearly massive, the kind of stars that burn brightly and briefly compared to smaller, longer-lived stars, like our own Sun. Their youth strongly suggests they formed relatively recently and relatively close to where they now orbit, directly contradicting the very physics that should have prevented their formation in that location in the first place. Scientists have proposed several possible explanations for this puzzle, though none of them has been confirmed with the same level of certainty as the black hole's mass or its event horizon. One idea suggests that these stars may have formed farther away, in a somewhat calmer region, within a massive, dense cloud of gas that later spiraled inward toward the black hole, dragging its newly formed stars along with it before the tidal forces had a chance to destroy them. Another possibility involves the idea that, under certain rare conditions, a sufficiently large and dense enough gas cloud might collapse quickly enough to form a star before gravity manages to tear it apart, essentially outracing its own destruction in a narrow window of opportunity. A third, stranger explanation involves collisions. Some researchers have suggested that a portion of these unusual stars may not have formed from gas clouds at all, but instead resulted from smaller stars colliding and merging together in the extraordinarily crowded environment surrounding the black hole, where stellar density is far higher than almost anywhere else in the galaxy. A collision between two smaller stars, under the right conditions, could theoretically produce a single, larger, younger-looking star, one that would appear deceptively youthful despite actually being formed from much older material, smashed together under immense gravitational pressure. None of these explanations has fully resolved the mystery, and the debate among astronomers continues, refined by each new generation of more sensitive telescopes. What remains undeniable, regardless of which explanation eventually proves correct, is that the region surrounding Sagittarius A star continues to defy expectations in ways that go beyond simply confirming a black hole's existence. It behaves less like the quiet, empty space you might imagine surrounding something so destructive, and more like an unpredictable, chaotic environment capable of producing outcomes that our best models still struggle to fully explain. And there is something quietly unsettling about that uncertainty, something that sits beneath the surface of an otherwise fascinating scientific puzzle. Here is an environment shaped by gravity so extreme that it bends light, slows time, and crushes matter past every known limit. And yet somehow, within that same violent, chaotic region, young stars continue to appear, burning brightly in defiance of the very forces that should have prevented them from ever forming. It is a reminder that even after decades of study, even after finally photographing the black hole's shadow, the environment surrounding Sagittarius A star still holds mysteries that our current understanding of physics has not yet fully untangled. Think for a moment about what it might have looked like if you could somehow stand at a safe distance and watch this region unfold across enough time. Streams of gas, stretched and distorted by gravity beyond anything found anywhere else nearby. Stars racing along impossibly tight, fast orbits, completing loops in mere years rather than centuries. And scattered among all of that chaos, young stars burning brightly, having formed against every expectation in one of the most hostile environments the galaxy has to offer. It is not a quiet, empty void surrounding a distant, invisible giant. It is one of the most turbulent, unpredictable corners of the entire Milky Way, hiding puzzles that continue to challenge everything astronomers thought they understood about how stars are born. Given everything you now understand about Sagittarius A star, its staggering mass, its bent and slowed time, its violent, unpredictable surroundings, you might imagine it as a constant, roaring engine of destruction, tearing through everything nearby with relentless, visible fury. The truth, strangely, is closer to the opposite. For most of the time, astronomers have studied it. Sagittarius A star has behaved less like a raging monster and more like something eerily quiet, a silent giant, mostly at rest, doing far less than its staggering mass might lead you to expect. Here's the thing most people don't realize about supermassive black holes. Their destructive power depends entirely on having something nearby to destroy. A black hole with nothing close enough to fall into it produces very little in the way of visible activity, since it is the process of matter falling inward, heating up and radiating energy as it goes, that creates the dramatic displays often associated with black holes in popular imagination. Sagittarius A star, compared to supermassive black holes found at the centers of many other galaxies, currently has remarkably little material nearby to consume, leaving it in what astronomers describe as a dormant or quiescent state. This was not always obvious to scientists studying it. Other supermassive black holes across the universe, particularly those found in the centers of galaxies known as quasars, blaze with extraordinary brightness, sometimes outshining every star in their host galaxy combined, as enormous quantities of gas and dust spiral inward, heating to temperatures of millions of degrees before disappearing beyond the event horizon. By comparison, Sagittarius A star produces only a faint, comparatively modest glow in radio waves and X-rays, a small fraction of what a supermassive black hole is theoretically capable of producing if it had more material readily available nearby to consume. Think about what that contrast actually implies. The same object capable of bending starlight, warping time, and holding an entire galaxy's worth of stars in orbit around it, spends most of its existence in relative silence simply because it currently lacks enough nearby fuel to ignite the kind of dramatic activity seen elsewhere in the universe. It is, in a strange way, a reminder that raw power and visible activity are not the same thing. Sagittarius A star does not need to be loud to be significant. Its influence is expressed through gravity alone, quiet, constant, and completely independent of whether it happens to be actively consuming anything at that particular moment. But quiet does not mean entirely inactive. Astronomers monitoring Sagittarius A star over the years have observed something they did not initially expect. Occasionally, without any obvious pattern or warning, the black hole flares, brightening suddenly in X-rays or infrared light, sometimes by a factor of 10 or more, before fading back down to its normal dim state within a matter of hours. These flares appear to occur when small clumps of gas or dust drifting too close to the event horizon are suddenly compressed and heated as they spiral inward, releasing a brief burst of energy before disappearing beyond the point of no return. One particularly dramatic episode captured the attention of astronomers around the world. A mysterious object, given the somewhat unglamorous name G2, was observed approaching dangerously close to Sagittarius A star, and many scientists expected the encounter to produce a spectacular display as gravity tore the object apart. G2 turned out to be more resilient than expected, surviving its close approach largely intact, likely because it was a star surrounded by a dense envelope of gas rather than a diffuse, easily disrupted cloud. The event ultimately produced a far quieter outcome than anticipated, but it demonstrated vividly how unpredictable the environment surrounding a supermassive black hole can be, even for scientists who have studied it for decades. Here's the thing that unsettles many astronomers about this quiet, dormant state. Nothing guarantees it will remain this way indefinitely. If a sufficiently large cloud of gas or an unlucky star were to wander too close to Sagittarius A star in the future, the resulting display could be dramatically different from anything observed so far. Some theoretical models suggest that our own galaxy's black hole may have been far more active in the past, potentially blazing with the same kind of intensity seen in distant quasars, before eventually quieting down as the material surrounding it was gradually consumed or dispersed over millions of years. This raises an unavoidable, quietly unsettling question. If Sagittarius A star was once significantly more active than it appears today, and if flares and outbursts continue to occur unpredictably even now, what might trigger a much larger event at some point in the future? Astronomers do not currently see any evidence suggesting an imminent large-scale outburst, and the timescales involved in these processes tend to be measured in thousands or millions of years, far beyond anything relevant to a single human lifetime. But the fact remains that the giant at the centre of our galaxy, however quiet it appears tonight, is not asleep in any permanent sense. It is simply waiting, patiently, for enough material to wander close enough to feed it again. And so, the picture that emerges is neither the constant roaring monster of popular imagination, nor a truly harmless, inert object quietly minding its own business at the centre of the galaxy. It is something stranger, and in some ways more unsettling, precisely because of its unpredictability. A supermassive black hole, mostly silent, occasionally flaring without warning, its long-term behaviour shaped by forces operating across timescales far beyond ordinary human comprehension. Every star in the Milky Way continues orbiting it regardless, indifferent to whether it happens to be quiet or briefly, unpredictably awake. For a long time, one question quietly lingered beneath everything astronomers had learned about Sagittarius A star. Was our galaxy unusual? Was the Milky Way, by some strange coincidence, the one galaxy in the universe that happened to harbour an object this extreme at its centre? Or was this something far more common, hidden at the heart of countless other galaxies scattered across the cosmos, simply waiting to be discovered? The answer that eventually emerged reshaped how astronomers understood galaxies themselves, not just our own. Here's the thing most people don't realize about how this question was even answered. Studying the center of our own galaxy had already proven difficult enough, requiring decades of patient observation, specialized instruments, and an enormous international collaboration just to capture a single blurred photograph. Studying the centers of other galaxies, many of them millions or billions of light years away, seemed at first like an even more hopeless task. And yet, astronomers found a way, not by attempting to photograph these distant centers directly, but by applying the same basic technique that had worked so well right here at home, watching how nearby stars and gas moved, and calculating what kind of mass could explain that motion. One of the earliest and most convincing pieces of evidence came from a nearby galaxy called Messier 87, an enormous elliptical galaxy located roughly 53 million light-years away. Astronomers studying the motion of gas swirling near its center found that it was moving at speeds that could only be explained by an object with a truly staggering mass, billions of times that of our Sun, concentrated into an impossibly small region, just as Sagittarius A star had been found to be, though on a far larger scale. This was, in fact, the very black hole later photographed by the Event Horizon Telescope, alongside our own, providing dramatic visual confirmation of what motion studies had already suggested for years. As telescopes improved and techniques became more refined, astronomers began finding the same pattern again and again, in galaxy after galaxy, regardless of size, shape, or location. Spiral galaxies similar to our own, enormous elliptical galaxies far larger than the Milky Way, smaller, more modest galaxies that seemed unremarkable in every other respect. In nearly every case where astronomers had sufficiently detailed observations, the same basic signature kept appearing. Stars and gas near the center, moving in ways that could only be explained by an enormous invisible compact mass sitting exactly where the galaxy's structure converged. Think about how remarkable that consistency actually is. These galaxies vary enormously in size, age, shape, and history, separated from each other by distances so vast that light takes millions or even billions of years to travel between them. And yet, at the center of nearly everyone studied closely enough, sits essentially the same kind of object, differing mainly in scale rather than in fundamental nature. Some contain black holes only slightly larger than Sagittarius A star. Others harbor black holes billions of times more massive, dwarfing our own galaxy's central object so completely that comparisons become almost meaningless. But the underlying pattern, a supermassive black hole anchoring the center of the galaxy, appears to hold true almost universally. This consistency led astronomers to a conclusion that reshaped how galaxies themselves are understood. Rather than being a rare oddity, an unusual feature unique to a small handful of galaxies, supermassive black holes appear to be a fundamental, near-universal component of galaxy structure itself. Some researchers have gone further, suggesting that these central black holes may not simply exist within galaxies as passive occupants, but may actually play an active role in shaping how galaxies form and evolve over billions of years, influencing the distribution of stars, the flow of gas, and the overall structure of everything orbiting around them. Here's the thing that makes this idea genuinely unsettling once you sit with it. If nearly every galaxy contains one of these objects at its center, then the universe is not simply filled with stars, planets, and glowing clouds of gas, the comfortable, familiar imagery most people associate with the night sky. It is also filled, quietly and almost invisibly, with billions of these strange, surfaceless, light-swallowing points anchoring galaxy after galaxy across the observable universe, each one holding its own vast collection of stars in a slow, patient orbit that can last hundreds of millions of years. And this raises questions astronomers are still actively working to answer. How exactly do these supermassive black holes form in the first place? Do they grow gradually, over billions of years, by slowly consuming gas, dust, and occasionally entire stars, or do some of them form suddenly, born already massive, during the earliest, most chaotic periods following the beginning of the universe? Observations using powerful instruments, including the James Webb Space Telescope, have found supermassive black holes already fully formed in galaxies existing when the universe was less than 1 billion years old. A discovery that has left many astronomers struggling to explain how objects this massive could have grown so quickly, so early in cosmic history. What once seemed like a strange singular mystery unique to our own galaxy has revealed itself to be something far larger, something woven into the basic architecture of the entire universe. Sagittarius, a star, is not an anomaly. It is an example, one instance among countless others, of a pattern repeated across nearly every galaxy astronomers have managed to study in sufficient detail. Every collection of stars you can identify in the night sky, every faint smudge of light captured by powerful telescopes peering toward the deepest reaches of the observable universe, likely conceals, at its very center, its own version of the silent, invisible giant quietly anchoring our own galactic home. With the understanding that supermassive black holes anchor galaxies throughout the universe, it becomes worth turning the lens back towards something closer to home. Not towards Sagittarius, a star itself, since you already know a great deal about what sits there now, but toward what its presence actually means for us, quietly, personally, every single day of our lives, whether we ever think about it or not. Because the truth is that distant, invisible object is not simply an interesting subject for astronomers to study from afar. It is, in a very real sense, part of the machinery that keeps our entire galaxy, including our own sun, moving the way it does. Here's the thing most people don't realize about their place within the Milky Way. Our sun is not sitting still at some fixed location, quietly minding its own business, while the rest of the galaxy moves around it. It is orbiting, just as every other star in the galaxy is orbiting, tracing an enormous path around the same distant center that stars like S2 circle at far closer range. Our sun sits roughly 26,000 light-years from the galactic center, embedded within one of the Milky Way's spiral arms, moving through space at a genuinely staggering speed, even though nothing about sitting here on Earth gives any obvious sensation of that motion at all. To understand the scale of this orbit, consider how long it actually takes to complete. While Earth circles the Sun once every year, and the Moon circles the Earth roughly every month, our entire solar system, Sun and all, takes approximately 230 million years to complete a single orbit around the center of the galaxy. Think about how long that actually is. The last time our solar system was in its current position, relative to the galactic center, dinosaurs had not yet appeared on Earth. Entire eras of life, entire chapters of our planet's history have unfolded during a single loop around that distant, silent giant. This orbit is not some incidental detail separate from everything else discussed so far. It exists precisely because of the same gravitational influence radiating outward from Sagittarius A star, combined with the collective gravity of every other star, every cloud of gas, and every hidden pocket of dark matter scattered throughout the galaxy. The supermassive black hole at the center does not act alone in shaping this vast rotation, but its presence, anchoring the very heart of the structure, plays a meaningful role in the overall gravitational architecture holding the entire galaxy together, arm by arm, star by star. Think about what that really means for something as small and personal as your own existence. Every sunrise you have ever watched, Every night sky you have ever looked up at, every quiet moment spent wondering about your place in the universe, has occurred while our entire solar system was slowly, silently completing its 230 million year journey around a point 26,000 light years away, a point with no surface, no light of its own, holding the mass of over 4 million suns compressed into a space smaller than our inner solar system. You have spent your entire life in motion, orbiting something you have never seen, and likely never will. Here's the thing most people don't realize about how gravity operates across such enormous distances. It does not require contact, communication, or any physical connection between objects to exert its influence. Sagittarius A star pulls on our Sun across a distance of 26,000 light years, using nothing more than the fundamental curvature of space itself, the same basic phenomenon that keeps you pressed gently against the ground, or keeps the moon faithfully circling the Earth. Distance, however vast, does not diminish gravity's reach. It simply weakens its strength, while the influence itself persists across scales the human mind struggles to fully absorb. And there is something worth sitting with, quietly, in this realization. The stability of our entire solar system, the reliable rhythm of day following night, season following season, year following year, exists within a much larger, slower rhythm, one governed in part by an object so extreme that it bends light, warps time, and swallows anything that strays too close. We tend to think of stability and danger as opposites, yet here, at the scale of an entire galaxy, they are woven together. The same distant gravity capable of destroying anything that ventures too close is also, in its own way, part of what holds our galactic home together, keeping billions of stars, including our own, moving in the same patient coordinated dance. Think, too, about the strange comfort hidden within that idea. You are not simply living on a planet, orbiting a star, floating somewhere in empty space. You are part of a vastly larger structure, one stretching across 100,000 light years, held together by forces anchored at its very center. Every person you have ever loved, every person who has ever lived throughout the whole of human history, has done so while embedded within this same, slow, silent orbit, carried along together, without exception, around a point none of us have ever seen with our own eyes, and yet one that quietly shapes the very shape of our galactic home. And so, the black hole at the center of the Milky Way is not simply a distant curiosity, confined to scientific papers and blurred hard-won photographs. It is part of the reason our galaxy holds the shape it does. Part of the reason our Sun follows the path it follows. Part of the enormous, patient architecture that has allowed stars, planets, and eventually life itself to exist in a structure stable enough over billions of years for something as improbable and fragile as you to eventually come into being, look up at the night sky, and quietly wonder what might be holding it all together. So here we are, at the end of a journey that began thousands of years ago, with someone standing in the dark, looking up at a pale, hazy band stretching across the sky, having no idea what they were actually looking at. We have followed that same faint glow through myth and misunderstanding, through the invention of the telescope, through a young engineer trying to fix static in a telephone line, through decades of stars traced patiently across the sky, through a photograph that took a network of telescopes spanning the entire planet to finally capture. And at the center of all of it, we find something that still, even now, resists being fully understood. Here's the thing most people don't realize, even after learning everything we have covered tonight. Knowing the mass of Sagittarius A star, knowing the size of its event horizon, knowing how it bends light and slows time, does not mean we truly understand what it is. We can describe its effects with a remarkable precision. We can predict how stars will move around it, how light will bend near its edge, how time will stretch for anything that dares approach, but The object itself, the crushed, infinitely dense point resting somewhere within that boundary, remains as mysterious to us today as it was to the astronomers who first detected a strange, unexplained hiss in the direction of Sagittarius decades ago. We will, in all likelihood, never travel there. 26,000 light-years is not a distance any spacecraft built by human hands could realistically cross, not within a single lifetime, not within 100 lifetimes stacked one after another. Even if we somehow found a way to travel at speeds approaching light itself, the very act of approaching Sagittarius A star would mean watching the rest of the universe age around us, decades and centuries slipping by, while our own clocks crawled forward at their own strange, dilated pace. It exists for us, and likely for every generation that will ever come after us, purely as an idea, a number, a shadow captured in a single, hard-won photograph. And yet, despite that unreachable distance, despite knowing we will never see it directly with our own eyes or stand anywhere near its boundary, Sagittarius, our star, has never once stopped shaping our lives. It has been there, quietly anchoring the centre of our galaxy, since long before the first star that would eventually become our sun ever began to form. It will still be there, holding the same patient influence over the same slow spiralling arms of stars, long after every person alive today has lived out their life and returned to dust. It does not know we exist. It does not need to. Its gravity reaches us regardless, indifferent, constant, entirely unconcerned with whether anyone is watching. Think about what it means to spend an entire life, an entire species, entire history, orbiting something we cannot see, cannot visit, and can only partially understand. There is something almost humbling in that thought, once you sit with it long enough. We build telescopes, we calculate masses, we photograph shadows cast by light, bending around darkness itself. And still, at the end of all that effort, we are left holding only a fraction of the full picture. A fraction that somehow feels both remarkable and quietly insufficient at the same time. We know more about the centre of our own galaxy than any generation before us. We still do not, and may never, know everything there is to know. But perhaps that incompleteness is not something to mourn. Perhaps it is closer to the truest thing this entire story has to offer. We are creatures who evolved on a small, quiet planet, orbiting an ordinary star, itself slowly circling something far stranger and more extreme than anything our ancestors could have imagined when they first looked up and noticed a faint glow towards Sagittarius. And despite our smallness, despite the impossible distances involved, we found a way to detect it, to measure it, to photograph its shadow, to understand, at least in part, what has been quietly governing our galactic home since long before we ever existed to wonder about it. We are, in the truest sense, the universe noticing itself. Every measurement taken, every photograph captured, every long night spent tracking a single star's impossible orbit around an invisible point has been the universe slowly turning its attention inward, using minds built from the same stardust that made Sagittarius A star possible in the first place, to understand its own strange and beautiful architecture. You lying quietly right now, listening to these words, are part of that same unbroken thread, a tiny temporary piece of a universe curious enough about itself to build telescopes, cross oceans of data, and stare directly into the dark until something finally looked back. So the next time you find yourself outside on a clear night, and you tilt your head back to look up at the stars, take a moment to find that same soft, hazy patch of sky towards Sagittarius, the one ancient priests once aligned their temples with, the one sailors once used to navigate without understanding, the one that quietly hides, 26,000 light-years away, the silent, surfaceless heart of our entire galaxy. You will not be able to see it directly. No one ever will, but you will know in a way that very few humans throughout history have ever known, exactly what is waiting there in the dark, patiently holding everything you have ever known in a slow, gentle orbit, that has lasted far longer than any of us could ever hope to witness. Thank you for spending this time with me tonight, drifting through the story of the quiet giant at the center of our galaxy. If you found yourself carried along by this journey, consider leaving a like or subscribing, so more nights like this one can find their way to you. And now, as your thoughts begin to slow and the weight of sleep settles gently over you, let yourself rest knowing that somewhere far above you, the stars are still turning slowly around a center none of us have ever seen. Sleep well tonight, and keep looking